Hi, this is Adam Griffin with the second video for this week. So this question is going to be number 53. So we have to find how much work is done by gravity when the separation of two objects with masses m1 and m2 changes from x1 to x2. And we're assuming that x2 is less than x1 because it's moving closer. So we have this equation where it tells us the force of gravity with a distance of separation represented by x. So we have force equals our gravitational constant times mass 1 times mass 2 divided by our distance squared. So for part A, we have to find the work done by gravity, and for part B, we have to see if one mass is much greater than the other, the larger mass stays essentially at rest while the smaller mass moves towards it. Suppose a 1.5 times 10 to the 13th kilogram comet is passing the orbit of Mars and heading straight for the sun at a speed of 3.5 times 10 to the 4th meters per second. What will its speed be when it crosses the orbit of Mercury? And then we look in the book and we can find a bunch of distances and masses and all of that stuff to plug into the equation, which I have written later down. So it also gives us our gravitational constant, which is 6.63 times 10 to the negative 11th Newton meters squared per kilogram squared. So for part A, we are finding the work done by gravity. So work is equal to the integral of force from our first distance to our second distance. So we know that force equals gravity times mass 1 times mass 2 over x squared. So when we integrate that, we get our work equals, and then our equation for work, which is gravity times mass 1 times mass 2 over x1 minus gravity times mass 1 times mass 2 over x2. So this is integrated. This is the specific solution, not a general solution. So we can plug in x1 and x2 now. So for part B, we're finding the final velocity of the object. So we have our work, which is also equivalent to our change in kinetic energy. And this equation is in the textbook. So we have 1/2 of our first mass times our initial or our final velocity squared minus 1/2 times our first mass times our initial velocity squared. So here I have a bunch of the values and they're color coded so you can track them as I plug them in throughout the next few equations. So we have our first mass, which is given up here, and it's the mass of the comet. We have our second mass, which is the mass of the sun, and that's given in the textbook. We have our initial velocity given right here. I'll change to this cursor. And we have gravity also given in the problem, and then our first distance and our second distance. So we can go over here and we can plug in our constants for this equation right here, and we set it equal to this other equation, which we can also solve for because we have everything that needs to be plugged in. This one we can't solve for all the way because we don't have our final velocity, but once we do this, we find that our final velocity equals our initial velocity squared plus 2 times the work over our comet's mass, and if that's the square root of that. So when we plug that in, we find that our final velocity is 68,158 meters per second. So that is how you do problem 53, and thank you.